Okay, welcome back to a continuation here on the intro to limits idea. A couple things we're going to look at today. One, you can see the first thing is the existence of limits. And that will actually bring us to a statement here that we say the limit does not exist. D&E we'll use a lot of times for does not exist. You might have heard that term before if you ever watched Mean Girls. The Lindsay Lohan character, she says it as well in there, and it's in part of a math bowl, quiz bowl type of competition, and she does the limit does not exist. And actually, she has this kind of spatial. Trying to remember back to her calculus class, and it's a graph I'm actually going to show you here, or one similar to it. Okay, but we'll get to that. Maybe I'll even post a link to that little video there. Okay, so. Existence of limits, meaning we have one or not. So here's the first example. There's kind of cases where things don't exist. So this one here says the limit as x approaches 0 of the absolute value of x over x. What I'm not worried about is you understanding how did I come up with this graph. I want you to look at the graph again. And there's one thing missing here. There should be, I don't want red. There should be open circles there. On this graph that I made this on, it did not include them, so I have to include them. It should be open circles because there is no point at 0. If you put in 0, you get 0 over 0. It doesn't work. So as the limit approaches 0, so if we go with our little guy idea, I'm getting closer. I'm always at -1 every time. -1, -1 as I go on this side. But up here, what value is it? It's always 1. Okay? The problem is it's going towards two different values, okay? It goes towards two different values, not the same value, all right? We'll condense this all in the end, but they have to be, on the left and right, be going towards the same value. So we say D and E does not exist, okay? So that's the first case. Again, I'll wrap this up at the end with a little bit of like notes in terms of what are the cases. But this is the first one where it doesn't go towards the same value. On the left, we're going to -1, and on the right, we're going to 1. Next section we'll actually talk about that we can look at those limits separately. The limit of this one, the limit of that one, and separate it. But overall, the limit does not exist. All right, next case. Limit as x approaches 0 of 1 over x. Actually, this is, I believe, the graph that Lindsay Lohan is thinking about that's on the board. So as we approach again, as we're approaching 0 on the right, what y value am I going to? Well, I'm not going to any, right? This just keeps going because there's asymptotes here, right? We have an asymptote right there. And it just keeps going towards infinity, right? This just goes and goes and goes. It doesn't stop. And then the same thing here, it's going towards negative infinity when it goes this direction. The term we use here, and the problem is we use the term it's unbounded. In other words, it doesn't go to any number. It's not so much that one goes to infinity and one goes to negative infinity. That's a problem. But it's that they go to either. Okay? I'll show you an example in a minute. So it's the fact that it doesn't go to any specific number. It just keeps going and going and going. Okay? So we say the limit does not exist. Number 3 is the same thing. My only reason for this example, as x approaches 0 again, I'm going this direction, this direction. I just wanted you to see that both sides in this case are going towards infinity, but that still does not mean the limit exists. That doesn't mean, oh, then we can say it's infinity. No, it's not a number. It's unbounded. All right? I just wanted to make sure that we understand in those two cases there. In other words, if you take the limit at an asymptote, it doesn't exist. And one thing I want to say, it's saying at this point it doesn't exist. It doesn't mean anywhere on this graph. In other words, if I asked for the limit as x approaches 1 of 1 over x squared, there is a limit. It's right there, right? It's going to be equal to 1. Because if I make little guys go here, I'm going to put armless guys, and I go closer and closer here to 1, I'll be closer to the y equals 1. All right, so it just means it doesn't exist at that point of x equals 0. Okay? And then the last one is a strange graph you've never seen before, but what's happening is, so this graph, as we get closer and closer to 0, this graph is like, I like to think of it as like, it's like really going up and down here, and then So when we go in from left to right, it's oscillating between values. It just is oscillating here. If we zoom in, you're going to see the same thing over and over and over again. It's just bouncing back and forth. This doesn't happen a lot, all right? But we still say the limit does not exist. And I'm not going to make you memorize like, oh, what kind of functions are those? No, it's about looking at graphs. And again, it's only at that point at 0. Out here, there's a limit. Here there's a limit. But it doesn't because it oscillates. And they're strange graphs. They kind of occur when you have a trig function with a rational function inside. That's the kind of thing, but you don't need to know that. Okay? So putting it all together, there are 3 cases when a limit does not exist. We say D and E. If f of x approaches a different number from the right side of c than it approaches from the left. In other words, they're going towards different values. Right? One was positive 1, one was negative 1. If the function increases or decreases without bound, and that occurs anytime we're taking the limit at an asymptote. In other words, it goes to infinity or negative infinity, but there's that term without bound or unbounded. And then finally is the strange case when f of x oscillates between 2 fixed values. We don't see that a lot, so it's not one that comes up. It's 1 and 2 that are more prevalent in your study here and in calculus. In fact, I don't think too often you look at graphs like the ones that occur for number 3, but it is a case that it doesn't exist. All right, so look, hopefully after working some stuff out in the book in the first part, and now I'm talking about things not existing, I'm hoping you're looking at that and saying, well, there's got to be a way. Like, I haven't really algebraically figured out those limits, and maybe you're starting to figure it out a little bit, but we're plugging in numbers, we're graphing, we're using the table feature. Like, that's not what we normally do. There's got to be a way to solve and find limits, and there is. In many cases, you can just use direct substitution to find the value of a limit. The very first example we looked at, if you plugged in 2, or was it 4? It was 4, you would get the answer of that limit, okay? So direct substitution works in many cases. So a lot of times, and what we say here, is the limit as x approaches c of f of x is equal to f of c. In other words, you just plug c in. When can we do that? Well, I love this term. This comes from our book. I've never saw it before, but I love it. Well-behaved functions. It's like, good boy, good function. You're a good boy. Okay, you're well-behaved. Well, what kind of functions are well-behaved? Well, polynomial functions, any polynomial. Well, that's like, x squared minus 2 and 3x to the 4th minus 3x squared plus x minus 9. Those are all polynomials. Rational functions with non-zero denominators. Well, what that means is rational functions look like this, right? X minus 2, x plus 1. If I'm finding the limit at a place that doesn't give me a 0 in the denominator. So in other words, if I plugged in -1, if I was finding the limit -1, I can't do it. But 2, yeah, as long as I don't get a 0 in the denominator, it's well behaved and I can get an answer. All right, so that's what we're going to use in terms to solve for some limits. So then, next section, 11.2, and we got some more stuff to do in this one, some properties and things, is, okay, so how can I maybe manipulate or change a function to make it well behaved so I can use direct substitution? All right, so what's going to happen is we're going to teach you a couple things, and we're not going to go too far. I'll let calculus do even more. Basically, if you're given, from this point forward, you're given a limit problem, and the first thing you want to try to do, direct substitution. If you get an answer, you're done. If you don't, you get something undefined. Well, next section I'm going to teach you how to manipulate some functions a little bit, things you already know, algebraic, and to solve it then by direct substitution afterwards. If that doesn't work, the other option is a calculator, graphing, those types of things at this point. You'll learn other techniques and things next year. All right, so a couple things here properties-wise in terms of limits, and this one I'm not too concerned about, but the idea is direct substitution. I'm actually going to start with the number 2 first. Limit as x approaches c of just x. Well, that limit is just going to be c. In other words, I plug in c, I get c. Whereas number 3, I plug in c, I get c to the n, and then c to the nth root of c, or the nth root of c for that one. The idea here is what we're going to talk about next is we can kind of break apart limits just the way you would think. And so that they would maybe look like these things and show you, as long as they look like this, we can just plug in. This is a constant, this is some number, so there's nothing to plug in as c, so the constant just gives you that constant back of b. Okay, so that's the idea. So a couple other property things is operations with limits. And to be honest, limits behave the way you would think. Okay, so let me set this up for you. We have the limit as x approaches c of some function. We're going to say it's L. Limit as x approaches c. In other words, it's got to approach the same number of some other function is k. That's its value, whatever it is. I'm going to go to number 2. And what we're saying here is if I had a limit and I was adding two functions or subtracting two functions, all I really would need to do is add or subtract the values we get for those individual limits of those functions. Okay, so in other words, they behave the way you would think. So like number 3 would be L times k, number 4 would be L over k, and then 5 would be L to the nth. Okay, I'm going to go back to number 1 because b is some number, a constant, and what this is going to be is b times L. In other words, it's almost as if we can pull the b out. And in fact, I think next year in Calc you may talk about that being more of the case. And so then you get b times L. Okay? Don't get too crazy with this. I think it just, you'll see the examples I'm going to do for these types of things. It's pretty easy. So I'm not too worried like memorizing this or that kind of thing. It's just kind of working with limits the way you would think they would work or behave. So these 4 here, giving you a limit. You don't need a graphing calculator, you don't need a chart, you don't need anything. You're just going to try direct substitution first. So we plug in 2. We get 2 to the third. Oh yeah, that's 8. Good, there's my limit. Okay, do number 2. 8 times 4. 32, yep, that's the limit. 32. Okay, this one here, tan of pi over pi. Well, you might need a calculator on that one. If you do, change it to radian mode since the pi. Or if you want to remember your trig, tangent of pi, let's see, unit circle wise. Let's see, pi, here's my unit circle. Pi is right there. What's that ordered pair? -1, 0. Tangent is y over x, so that's 0 over -1. So that's 0. Oh, okay. So that's 0 over pi, which gives me 0. Okay. And then the last one, 16. 4th root of 16. Well, that's just going to give you 2. Okay. So direct substitution. That's all it is. If I'm going to give you some problems there, that's what you do. You just plug in. It looks complicated, right? Limit as x approaches 2 of x to the cube. All you're doing is plugging in a number. Algebra 1, basic substitution. Okay? All right. A couple more. Limit as x approaches 1 of x squared minus 2x plus 5. So that's 1 squared minus 2 times 1 plus 5. We got 1 minus 2 plus 5. So what's that, 4? Yeah, it's going to be 4. Now, here's an example. This is rational. Doesn't always work. There's asymptotes and things involved on this one, right? Stuff that holes, all those kind of things. But first thing you want to do is plug in 0. See what happens. Well, on top I get a 1. On the bottom I get -4. So there's my limit, -1/4. So plug it in. You get an answer. As long as you don't get a 0 on the bottom, you can solve it. All right, last thing is kind of using those properties. All right, so here's what's going to happen with these problems. I'm going to give you some limit as x approaches c of a function f of x. I'm going to give you an answer. It's 5. I'm going to give you some limit as x approaches c of another function, g of x, and it's -3. And I'm going to ask you to do some different things with the notation. So like this one is limit as x approaches c of 5 g of x. What does that mean to do? Take 5 times the limit of g of x, which is -3, and that's -15. They behave the way you would think they would want to behave. There's not like it was with logarithms and all that. Okay, this one here, f of x minus g of x. We'll take the limit of f of x, subtract the limit of g of x. That's 5 minus -3. That's 8. And that's it. All right. So I'm going to give you some problems on that. Most of it's pretty easy direct substitution, some dealing with these kind of properties. All right. As usual, if you have any questions or problems, let me know.